The first category of function that we'll take a look at is the linear function. Suppose we have a pool that contains 200 gallons of water, and then we start pumping water into it at a constant rate of 5 gallons per minute. We can look at this situation in a few different ways. From a numerical perspective, we could form a table containing the data for the first few minutes. At time 0, we were told that the pool contained 200 gallons of water, and then 1 minute later it would contain 205, and 2 minutes later 210, and so on. Each minute that passes, 5 more gallons of water are added to the pool. The graphical perspective doesn't differ much from the numerical. The bold blue dots are exactly the same as the data points that we saw on the table. After 0 minutes, the pool contains 200 gallons. After 1 minute, 205 gallons. After 2 minutes, 210 gallons, and so forth. Since each minute adds exactly 5 gallons to the pool, the points of data are fit perfectly by a line. The line has the advantage of helping us visualize how the gallons are changing over time. It also provides information about times that don't appear in the table, such as 30 seconds. From an algebraic perspective, we'd like to create a function that relates time to the water that's currently in the pool. Let's write the data in a slightly different way. At time 0, there are currently 200 gallons that we began with, and we haven't yet pumped any new water into the pool. So that's plus 5 times 0. After 1 minute, we have the 200 gallons that we began with, but we also have 1 minute worth of water being pumped into the pool. And since that water comes at 5 gallons per minute, that's 5 new gallons that we've added. So after 1 minute, we have the 200 gallons we began with, plus 5 gallons that came in for 1 minute, so 5 times 1. After 2 minutes, we have the 200 gallons that we began with, and we've been pumping water at 5 gallons per minute for 2 minutes. So we have 200 gallons plus 5 gallons and plus another 5 gallons at the second minute. Or shorthand would be to say that we have 200 gallons plus 5 gallons times 2. Writing the data in this way suggests a function. The number of gallons in the pool after t minutes is 200 plus 5 times t. That is, the 200 gallons we began with plus 5 gallons for each minute that we've left the pump on. So this is a good example of a linear function. Linear functions model data that demonstrate repeated addition of a single value. Our single value here was 5 gallons. Each minute we wait, we add another plus 5 gallons to the total water that's in the pool. Another perspective is to say that a linear function is one whose graph is a line. This comes about because every time we move to the right 1 minute, we move up 5 gallons, no matter where we are in the graph. A third viewpoint is that a linear function is one that can be expressed as f of x equals b plus mx. And in this viewpoint, I mean that b is the initial value. So our value of b was the 200 gallons of water we began with before anything took place. And m is the constant rate of change. It's the constant 5 gallons that we add each minute. The value of m is also called the slope because it affects how steep the line would be if we view the graph of the function. Let's look at this same example in a slightly different way. Suppose instead of having the description of the scenario that we started with 200 gallons and add 5 gallons every minute, instead we just have the data here presented as a line. How could we find the equation that describes this line? Since the graph is a line, I know a linear function is appropriate. And so I can begin by saying that the equation should look like f of x equals b plus mx. But I need to determine the particular value of b and m that I should be using for this line. I can see from the picture that the initial value should be the 200 gallons, because at time 0, I have an output on the graph of 200. So the value of b should be 200, and I can update my function to say f of x equals 200 plus mx. M is the amount that I add each time I move forward one step in time. So I might compare time 0 when I have 200 gallons to time 1 when I have 205 gallons, and see that that's a net change of 5 gallons. In fact, I could compare any two adjacent values and find the same rate of change. If I compare 3 minutes when I have 215 gallons to 4 minutes when I have 220 gallons, I still see the plus 5 gallons per minute. So this tells me the value for my slope should be 5, and that my function is now f of x equals 200 plus 5x.